Today here on the bench we have a Yaesu FT-757GX. So this was really a nice radio in its years. Now it is quite old and well, it is not in the best cosmetic condition. But you know, I thought this might be a good example for what can happening when you try to do some adjustments and alignments by yourself. And it is furthermore a good example because you know, we do not get any spare parts for this radio anymore, and so I thought, okay, let's go and make a video on this, because this radio came in, and well, the old man told me that he tried to make some alignments inside, and well, then he has broken you know, the little ferrit of one of the little RF transformers, and you know, we do not get any of the spare parts, and yeah, therefore it could be interesting if we will be able to fix it, maybe with some nice ideas, so I don't know. Well, I would say let's crack it open and see what really happens, and then let's go and check if we can fix it, or if this radio is lost because we do not get the needed spare parts. Yeah, I've just cracked it open, and let's get rid of this shielding here. And well, the old man told me that he tried to you know, do some alignments, and can we see it? No, but yeah, let me do it this way. Yeah, you can hopefully see that. Let me go a bit closer, and maybe you can see that we have here a transformer where the ferrit is missing, because it braked down, so it cracked when he tried to do the alignment, and now as you can see, it should look like this here. So you see the little ferrit inside, and here it is completely gone, and yeah, that is the reason why the oscillator which is connected to it, or yeah, let me call it, it is a part of a quartz oscillator, and that is now not working any longer, and yeah, we need to find a solution that we can bring it back to work. Okay, so next will be to disassemble the complete local unit. So therefore I have to take off all the wiring, and then I have to take off all the screws, and then I can take out the board that I come to the solder side to get this inductor out. So that will be next. Okay, so next will be to disassemble the complete local unit. So therefore I have to take off all the wiring, and then I have to take off all the screws, and then I can take out the board that I come to the solder side to get this inductor out. So that will be next. Yeah, our board is out, and yeah, you can believe me, that is really a pain to get it out. So anyway, now we have the possibility to unsolder it, and then we can measure it, and that will be next. Okay, it is unsoldered, and now we can take it out. Here it is. Okay, and yeah, as we can see, we have some more pins here at the bottom of this inductor, and as we have seen it in the schematic, there should only be 2 wires connected to all these pins, and that is what we need to find out, and then we can measure it. Yeah, this way we should be able to see it. Now it is on macro, and yeah, so all the pins are obviously not connected, but what you can see down there is a wire obviously connected, and we have a wire connected here. So that means this both pins seems to be the live pins, and all the other pins are not needed, except that this both, because this is ground, and that is important for shielding. But yeah, these both are our connected wires. Okay, the inductor is connected to the meter, and what we can read is that we have obviously a conductor of 8.8 microhenry. 8.8 microhenry, and that is now a value we need to find to bring it back into the circuit, and hopefully we can get it working again. But remember, with a ferrit inside, the inductivity will change. So this is now without any ferrit inside, and that means we need to find an inductor which comes very close to this value without a ferrit inside, and that is what I have to look for if I have somewhere a little inductor which could fit. Yeah, I've taken it apart, as you can see here. So we are able to take this shielding off, and then we have normally here the body, what we have. The body is, normally it looks like this, what we have here. So normally there is a body where you can put your windings on, and then in the middle you have your ferrit, and then if the winding is done and the wanted value, in our case for instance 8.8 microhenry or so, then well, you take such a housing which you can put then over the body, and then the shielding is done, and well, then you can use it in your circuit. But in our case, I thought I thought I can fix it, but as you can see here, so that is the inner plastic which was the body, and yeah, it is broken out, so we cannot fix it anymore. And yeah, you can see down here, let me go a little closer. That is too much, but yeah, so it should work. Yeah, you can see here the little coil, right, which is yeah, the winding itself is producing our 8.8 microhenry, but yeah, I have no chance to put back here a ferrit or whatever, because yeah, the inner construction is broken. So yeah, that is really a pity, but well, still the challenge to find a way to replace it. So maybe I can find a housing in the same size that I can try to put winding on it, like this. If this can't be used, so you simply can see the dimensions doesn't fit. So have a look. So no chance. I cannot get this into the circuit. But what I would really like to have is a body like this, where we could put on the windings to get without ferrit 8.8 microhenry, and then we could check it in the circuit. So that would be great. And if I'm not able to find anything like this, yeah, then I have to contact some friends, maybe that they have still some spare parts. I personally don't have this special guy. So yeah, let's see what we can do. Well, to be more sure what we have here on this little body, I just hooked on my meter again, and well, without our housing, our shielding, I'm measuring again, yeah, our 7.5 microhenry, and we measured before. We measured before 8 point something. You know, but what we do not really know is if the windings, if the wire is already on ferromagnetic material, and that would have an impact on our inductivity. So what we need to know is if this body, or however you want to call it, does already be something ferromagnetic, and the only way to find out is to take the wire away from this little body and put it on a plastic, yeah, whatever, and then measure it again, because if we want to reproduce inductivity which is close to what we have measured here, we need to know what we have, and therefore we need to know if you know, the material which is used here does not change the inductivity of the winding itself, or if it already have an impact on the inductivity. So that is now very important to go ahead. Well, as it is more than difficult to get an original spare part for our inductor, I am currently, or still, or whatever, looking for another solution, and therefore I cracked another inductor open, and what I was able to get is this winding body, which was originally in this guy, which I have cracked open. And well, this is our original shielding, and out of the shielding I have taken the rest of the plastic inner material. So that is what I've taken out, and so we do not need it anymore. So now have a look. It is possible to fit this body into our tin, into our shielding. And on the other hand, we are able to fit it on here, so that that fits here onto our base, which we need to solder it back in. So the plan is now to cut carefully this clips here away, because we do not need these clips here any longer. And then maybe, so we have to test it, but maybe we can glue it here on our base. And then, well, I have a ferrit which fits in here. So, you know, that is what we need to do the final alignment when it is back in our circuit. And yeah, as I said, the plan is when it is when these clips which we can't use are cut off, then I will try to glue it here onto the base, and then we can do our windings. And well, what I want to check first is I will take our original wire, which is on this little, whatever it is, carrier. Let me call it carrier. And I will wind the original wire to this body here. And then we can test the inductivity when it is here on the body without the ferrit, to see what the inductivity is, because then we know if this little body here already is ferromagnetic material. So that is important, because if it is already ferromagnetic, then we have to increase our winding here on this coil to get our needed inductivity. And well, but you know, this is still critical enough, because if we have too many windings here on this body, then we will get we will have automatically problems to fit the body here into our shield housing. So a lot of things what we have to explore, but maybe that our plan will work. Okay, we will see. Yeah, I've taken off the wire from this little carrier, where we don't know what the material is, and I put it here on the coil, or on this body, better on this body. And on this body it was 15 windings, and without the ferrit inside, it was somewhere in the nano Henry area. So that means this little material is a strong ferromagnetic material, because now I have 20 windings on this body made from this coil wire right here. And yeah, as I said, I put 20 windings here onto the body, and I put the ferrit into the body. And what we can read here right now is 4.5 microhenry. And we know that we need something around, somewhat around 7.375 microhenry. So that means I have to increase the windings here on the body, that I will come close to, let me say, 8 or 9 microhenry with the ferrit completely inside. And when I then screw the ferrit out of it a little bit, then the inductivity will drop down, and that is what we need, because we know with this little body we were somewhere around 8 in the housing, so that is what we did first, and there we was somewhere around 8.5. So that means with the broken ferrit which was on top of this, I guess that the original value were somewhere around 10 or maybe 11 or 12 microhenry. So what we would like to get is that we can adjust the inductivity somewhat around 8.5 microhenry up to, let me say, 12 to come into the area where the old and original one was working. So therefore, I guess I will double the windings here on the body, so that we get to, I hope, 10 or 11, because once again with the ferrit inside we have now 4.5. So if I double it, maybe we are around 9. So now maybe it is better to put somewhat around 50 windings here onto the body, and then we will check. And as I said, with the ferrit completely inert, we should, my guess is as good as yours, and I would guess that we need somewhat around, I don't know, 12 microhenry. So is that the value which it was originally? We don't know. So the only thing we know is that this little carrier was already ferromagnetic, and then remember there was a second ferromagnetic material over it, which we know is broken down, and we absolutely don't know what the original maximum value were with the second ferrit which is now broken. So the only thing we can do, we can try to come close to the values we guess, but we don't know. So let me try to put 50 windings onto the body, and then let's measure once again the inductivity of what we have then here on the bench, and if it comes close to 12 or I don't know 13, then we should try to glue the base or our what is it, where we can solder it back into the circuit. And the only way is to check if it works or not. So it is only try and error what we are doing here so far. I have now approximately 40 windings here on the body, and I brought now the ferret into a position where we have approximately our start our start value when we measured the inductivity first time. And well, when I now move this ferret into the body, so that means into the coil, then our value will change. Okay, not sure if I'm able to demonstrate it, but now I'm moving the coil. You see, this is a bit difficult. I'm moving the coil into the inductor, and what you can see, we can increase our inductivity by moving the coil, not the coil, sorry, the ferret into the body. So that means, well, into the coil. And we are able to reach a value of about 70 microhenry, and I hope that this is what we need. And the 17 where is our little coil? So it is down here, and yeah, what you can see is that under this condition, this condition, the coil is now almost in the body, and that means we have now adjusting range which starts approximately around 8 microhenry and works up to 20 approximately, and that should do it in the circuitry. So okay, let's go ahead, and yeah, I'm gonna try now to cut off here this clips that we can glue the body on the base, and then we want to try to bring it here into, let me call it housing. Well, as you can see, it is now glued together, and the tiny wires are already soldered to the base pins. Well, now I have to do some insulation here over the body, that when we put back our metal housing, that there will not be a huge influence. So I hope that altogether, yeah, we get it all under control. But yeah, next will be to wind an insulation here over it, and then let's try to get it back into the housing, and then we need to do another measurement and hope that we are close to that what we expect. Yeah, the insulation is no rocket science, so that is what it looks like. And now we try to put it back in the metal housing or the metal shielding, whatever you want to call it. And yeah, then let's hope that we have finally reached our target inductivity. Well, our last try failed. So we were not able to reach our target inductivity, But now I have an approach which might be really promising. As you can see, let's try if we can get it a bit more into the picture. What you can see here is that I have a hat. What I was able to put about or over the body, and this is already ferromagnetic material, and so this will already increase our inductivity a bit, and then we have of course our insert, which we have here, but well, this construction does not fit into our original shielding, so we have to use a bigger one, which is this here, and I can fit it in here, but as you see, we have to cut it down here a little bit, because the original one, you can see it if we compare it here. So the original one is not that big, so we have to cut it down a little bit. But more important is, of course, if this will fit into our circuit, and well, we have to put it down here, because this is the place where it have to go. And as you can see, this would really fit, and that is very promising. So maybe that we will be successful at the end of this game. But anyhow, let's test our inductivity if we are able to really reach our target value. So meter is hooked on, and yeah, shielding is on the coil, and well, we are now at our starting value, and have a look. So that is now 8.6 microhenry, and remember when we did our first measurement on that, let me go back to the value over there, so that you can watch this. And remember, that was really our first value. And when I now start, I hope I am able to show it. And when we now start to move the coil into it, you see we are really able to reach around 13 microhenry, and that should be our target value. I mean, that is still a try, but well, as we know, on this little, now we have a focus problem, of course. You may remember this little guy here, that was the material where the coil was winded on. And well, we measured our first value with 8.7 something, I don't know. So I think that when the old coil was already in good condition, I do not really believe that the value was much bigger than 13 microhenry, as we can read right now. So I hope that this value will be okay, and you can see we are not completely moved it inside, so there is still a little way to move. So yeah, let me crank it up, and once again now we are very close to what it's possible, and you see 15 microhenry, and that is very promising. So what I will do now is I really gonna cut down the shielding a little bit, so that our insert coil fits better into it, and then we want to bring it back into the circuit. And well, if I take the original tin, you can see that the ground leads, or whatever it is called, are very close together size-wise, so that should fit into the circuit as well. So that all is really very promising. And yeah, let me cut it down a little bit, and then let's bring it back into the circuit. And yeah, when we are lucky, it can really work. So I'm really excited how it will work. Okay, so this is a test if this housing fits into the free space. And well, if as you can see, it seems to work, so there is nothing in. So yeah, I can take it out, and you see, well, no problem. So we can go ahead with this approach. So I've already cut it down, so that this construction here fits better into it. And as you can see it right now, it is now cut it in the right way. So this should really be okay. And yeah, next will be put it back into the circuit, and then let's see how it works. Okay, have a look. Our home-brewed coil is in. So this is the solder side, and here we have it on the top side. So this is now our home-brewed coil. It is inside, it is soldered, and yeah, so let's go and put circuit back into the radio. And yeah, cross fingers, so I'm really excited. Ooh, all these wires here. That is a little bit scaring, isn't it? And well, we have to find the right connection points back. Okay, so let's try. Okay, and now the moment of truth. I have hooked on the radio to the communication tester, and it is hooked to the power supply as well. And now, let's see if it works. I mean, there is no alignment done yet, but yeah, the presetting was approximately what we measured before, so maybe that is good. So we are on 20 meter band, 14100. So okay, let's try. Okay, so it is on the 40 meter band, so let's go up to 14, and we are at upper sideband, and that means we need to dial 14099, and there we should receive our communication tester. So let's go up to 099 and hello. Hello. Hey, we have a signal. We have a signal. Great. Yeah, it is a little bit out of frequency, but that doesn't matter up to here because it is working again. So that means our oscillator, where the conductor was from, is working, and that is a success. And what you can see, okay, let's switch off the speaker and have a look. So we have a nice signal to noise ratio, and we have a nice and clean sine. So this is what we are feeding back to the meter, and that really means we have really a working circuit. And let us check what is our value. So we are on 941, so that means we are 60 hertz off, 60 hertz off, and that is simply to correct by a proper alignment. So now I'm really sure that we will be able to fix it. So now we have to start the alignment and see if we can twiggle all the filters to what we need to adjust it, and then the radio is back in service. So that is really great. Well, the good news is that we still have enough margin to change the value of the conductor. So you can see the kernel here. The kernel here is right in the upper position, so we really can turn it. And as deeper we throw it into this body, we crank the inductivity up, and that means from that point of view it should be no problem to adjust the radio to the required values. Okay, now we have to go through a bunch of settings which we have to check and to align, so that is really sometimes a very annoying job. But anyway, we have to go through to bring it all back into specs. For the moment in time, the counter is hooked on a test point, and we have now to adjust our reference frequency, which has to read 45 megahertz plus minus 20 hertz, and we have plus 36 hertz. So that means we need to adjust it, and you directly hear the changing tone in the background. So that really makes a huge impact. So now I'm trying to bring it into spec, and now we are very close to what it should be. Yeah, now you can see we are now very close to the setting which we expect. And yeah, so that is what I have to do right now. Go through the whole bunch of settings. So that will take a while, but anyway, it has to be done. And yeah, I don't want to film it because as I already said, it takes too long. So let us come up with a result, and then yeah, the radio will be ready to go back into service. Well, yeah, let's share this nice success. We are right now at the stage where we have to align this carrier point oscillators, and as you know, this here is our new coil, and I did a nice presetting of it, and the LSB carrier point we have to adjust with this guy down here, and we have to adjust it to 8.213 plus minus 50, and have a look what we have. So we have 8.213.398.2. So we are 18 hertz off, but that means we are still in the tolerance of plus minus 50 hertz, and that means that you know, the inductivity we are reaching with our new coil is sufficient. I mean, okay, now the margin is full used, so the kernel is right inside the body, so it is set really to the highest inductivity we were able to achieve. But anyway, in conjunction with this little capacities, these trim capacities, we are absolutely able to achieve the level which is mentioned in our spec, and that is exactly what we wanted. So that is really a nice success, and yeah, we really can be happy. So now I'm quite confident that we get the radio back to work. Well, I would say it is done. Yeah, let's switch out the annoying tone. Yeah, radio is to 14099, and so we have here 14100. We are in upper sideband, and as you can see, the reading is 6 hertz off, and that is really a nice value. So what does that mean? All the adjustments are done. Down here, that is our new coil, and it is now fixed with wax. so that it can't move anymore. And yeah, so the proof is that we are only 5 hertz off frequency. So that means the alignment is fully done. Everything is now back in good condition. So that means radio can go back to the old man, and yeah, hope that he can use it for another period of time. And yeah, and if this all made a bit sense to you, and if you think that was a nice video, please give thumbs up and catch you next time.